Thanks again. So I'm going to be, so the plan today is first I'm going to do a brief review of, okay, well, what happened yesterday? And then I'm going to talk about two topics which are sort of interrelated. One is invertible field theories. So I said some of this very fast at the end yesterday, which probably wasn't super helpful for anyone. So I'm going to say it in more depth today. So invertible field theories is a topic within mathematics. And so what you get out are actual, are completely rigorous theorems that say, okay, these objects in mathematical physics are classified with Bordism groups. So you compute some Bordism groups, what are they telling you? Well, one thing they're telling you is what are the possible invertible field theories in that dimension. And then an application to condensed matter, symmetry protected topological phases. So this part is, there's a lot more conjectures and a lot more things we don't know how to make into mathematics, which you might, it could be, well, that sucks, but it's also an opportunity to do things. So that's what I'll be doing for the next hour. As always, please interrupt me with whatever questions you have. I'm always happy to take questions. Last lecture was great. So that'll be this talk. The next talk this afternoon. So originally Miguel and I were going to do application, and then computation. But Miguel is feeling a little sick today, so he asked if I could give one of my talks today. So I'm going to do so the second talk will be computations part 1, and then Miguel will give computations part 2 later this week, along with 2 more applications. So that's the current plan. So first we want to recap. So fixing the kind of, I didn't give this the name. Let's say the symmetry type. So we said that we had a space and a map, psi, down to BO. So BO is the object that classifies vector bundles stably and virtually in rank 0. And so this can be used to encode orientation, spin, you could say, a principal G bundle. So fixing that, you can define Bordism groups of n-dimensional manifolds with Katayas structure. The idea is that manifolds and Bordisms have this additional structure, and they and the identification, the boundary of X is n disjoint mean n. This identification must be as manifolds with Katayas structure. So the sort of fundamental example is orientation. We said, okay, we just want to, the first example of Bordism, we just said, okay, manifold boundary. But what if this has an orientation and we want the induced orientation on the boundary to agree with the orientations of M and N that we've chosen? And there's the caveat that we have, incoming and outgoing, we use M here, and we use the opposite of N here, minus N. But just so that addition works, or sorry, inverses work. So we talked about how to do that. One thing which I think I didn't say super clearly last time is, or that's probably a little small. So this choice of psi structure, so the choice of symmetry type, is there to encode physics data that you care about. So let's say that you have, for example, a theory with fermions. So and also a G symmetry. So G is some ordinary matrix. I'm not going to try and make it any fancy right now. So it's, you might try and make a G symmetry into, you might want to strengthen this by saying, okay, I can couple to a gauge field for this symmetry. So you want this to make sense on manifolds which have a spin structure and also a principal G bundle with connection. So the connection is geometric information. So we have to, unfortunately, we have to throw that out when it comes to defining this. But then we would say that B is the classifying space of spin BG. So BG gives us that out of a principal G bundle, and then B spin says, I want to put a spin structure on the tangent bundle. The classifying map of the tangent bundle should lift to something that, so the transition functions, instead of just being valued in ON, they should be valued in spin. And that's what this does. But there's a lot of other things you could do. Right, so I could take, let's say G is Z mod 4. So I have just this like order 4 symmetry. Maybe I'm rotating something, although that rotation doesn't act on space or space-time, it just does something internally. So one thing which you could do is you could say, so let's say X is the generator, symmetry group. Let's say that I have X fourth is minus 1 of the F. So this is no longer literally Z mod 4, right? In particular, it has order 8. So in that case, you get this group that has this structure. So you take spin and you take Z mod 8, and you identify the common Z2F subgroup and the Z2 subgroup here, 0 and 4. So the point is, so I have some symmetry, but it's, it doesn't quite close up. After I do it 4 times, I get fermion parity. So then what is psi? Well, what can I do? I can say, okay, well, let's quotient out by fermion parity. Let's kill Z4. And let's, SO includes an O. And this composition is psi. So the point of these examples is, I think I was a bit abstract about this, but you look at what are the symmetries in my theory, what are the fields, and then you write that all together, including how they interact, and that tells you what psi. So the point of considering all of these different flavors of bordism is not just to find more interesting math questions, but also because these are going to match whatever's going on in physics. Does this make sense? Do people have questions?
So you're saying that you look at the field content of your theory, yep, and you look for some domain wall that includes the field variation, that field variation. So that's why you have this extra structure.
I don't know about domain wall. I'm just saying,
I mean, in the interpretation that Irene gave yesterday of cobordism as a domain wall connecting to effective field theories, you're saying that also these fields need to vary, and that's why you have this extra structure.
Yeah. And so, but yeah, I think the key idea is like look at the field content, and that tells you what you need to do. So let's see. So
are you going to recall what invertible means?
Oh yeah, absolutely. Yeah, thanks for checking. But yeah, that also went a little too fast, and so I will slow down. More questions? So here's a bordism. And so I said a little bit about this last time, but I'm going to say it more slowly today. Oh, is this also a domain wall for the camera?
Yes.
Oh, okay. Thank you.
It's smaller, but yes.
Okay. Cool.
Let's sharper. It's not a thin domain.
Unfortunately, we can't bring the domain walls together or something. So let's say this. So we've been thinking of these bordisms as like making M and N equivalent in some way. Like manifolds, they're hard to classify, but if I can just allow these kinds of things instead of just diffeomorphisms, they get easier. But instead, I want to think of this bordism as data. So as some sort of function from M to N. I mean, it's not a function. A function takes a point here and gives you a point there. That is not what is going on. We're thinking of it as a function in some sort of weird sense. Maybe there's it's like some passage of data from M to N. Maybe it's time evolution from space to space. So that leads to the idea of the bordism category. Board N side. So everyone uses their own notation for this. So I compromise and pick something completely new. So it's the category whose objects closed n-1 dimensional and if side structures are still not your thing, you can think oriented or spin or manifolds with a principal Z2 bundle. So like it's just some topological structure, and I want to be able to do this for all of them at once rather than defining a new variant for every problem. So things like M and N are objects. And then the set of morphisms from M to N is the set of bordisms from M to N. So in other words, a bordism is in this category, a bordism literally is a function from M to N. So there's one little caveat, which is that I need to identify bordisms which are diffeomorphic when you fix the endpoints. And this is so that you get a category rather than an infinity category. If you didn't know what that meant, don't worry about it. It's an annoying thing about composition. So
if you don't fix that, if you don't identify that, you get higher categories, right?
Yes. So there's two different ways that you could do make this into a higher category. One of them, the typical extended TFT to get to implement full locality, you sort of extend downwards, and this is the other one. So it's sort of, it's the right thing to do in the end, but we're not it's for I don't think you gain anything from a physics perspective by thinking about it from the first point of view. In any case, morphisms are bordisms. There's some identification which is there so that I'm not lying to you. And that's like, oh, I need to be on the side of the line. More questions? Okay, so this has more structure. This is symmetric monoidal. That means it has a tensor product and it has a unit. And these obey certain axes. For example, the tensor product should be associative, it should be commutative. But in category theory, writing these things down takes more time. So there's a long tradition of saying, oh, the tensor product, it's associative up to natural isomorphism, it's commutative up to natural isomorphism, and then not saying what that means. I'm going to continue this tradition because honestly, we're not here for me to write a bunch of big diagrams on the board. But you can read about it in McLean's book, like what the actual definition is, and then you will understand why I didn't do it. But what symmetric monoidal means is you have a tensor product and it behaves like the tensor product in vector spaces. So the tensor product is disjoint union, and the unit is the empty manifold. And I remember being skeptical when I first learned this, but it turns out if you go through and carefully read the definition of manifold, the empty set works for any dimension, and it has a psi structure vacuously. So that's good because now we have a symmetric monoidal category. So if symmetric monoidal is not a word you're super happy with, you can just, well, again, it just means that we can multiply stuff together like in a grid. So complex vector spaces with tensor product is also symmetric monoidal.
One question.
Yes.
Where we have defined the bordism category, are we doing it specifying the dimension we're working in? Or it's like we did the other yesterday, so dimension by dimension?
So we fix a dimension N. I'm sorry, I definitely should have said that. And so when I say I fix the dimension N, it's the dimension of space-time. So if we're thinking of this as like space and then evolving, so then this bordism is space-time, and I say board N, meaning N is the space-time dimension. So I will say that usually when I talk to physicists, they get kind of grumpy when I say, oh yeah, space evolves when topology changes. But like if you're doing quantum gravity, apparently that actually happens. So it is what someone has told me. So hopefully this seems like a good metaphor for why this is like why we're doing this. Were there more questions?
If you think of about this as an evolution, how do you keep track of the direction of time, just by orientation?
So I guess the way I would say it is, so in a boardism, if I've said this is a boardism from M to N, I've identified one of these as incoming and one as outgoing. So time is already sort of built in. You might ask, okay, well, do I know what time is on every slice? And then you want to add more structure. But yeah, yeah, it's sort of a weird question. Like a lot of this stuff is relativistic from the beginning, but then when you sort of cut it up, it becomes like it's sort of breaking this relativistic symmetry. I don't actually have a good answer to that.
I mean, at least in the TFT definition, I think it's normal because when you define TFTs in a Hilbert space formulation, you need to specify like a foliation of
Yeah.
space.
Yeah, that's true. I don't know, this will come up later in the condensed matter bit, actually. Like the fact that like you can't just sort of play fast and loose with relativistic symmetry. Or at least I can't.
Yesterday you also mentioned that there's this notion of extended TFT. Where
Yes.
You don't just simply cut it this way and then.
Right. So that's one of the ways of adding higher categories. I think it's a good thing, but it's probably not the right thing to do in this talk. If you want to know more about it, or anyone wants to know more about it, I'm happy to talk about it as best as I can.
I just want to say that does that restore this relativistic symmetry? I mean, the symmetry of.
So the problem is not that I didn't cut in enough directions. The problem is that I picked an arrow of time.
Okay.
So I don't think that's the place where I understand this problem the best is in the condensed matter setting, and that does not fix this problem. Yeah.
But I think again, if we go back to this domain world realization of what a boardism could be, then you have a like variation of the fields along one direction.
Yep.
And that's what it is, a solution that breaks the symmetry. So that's fine.
Yeah. Okay, that's a good point. Yeah, I mean, I'm honestly, from my perspective, learning all this stuff sort of upside down, starting with the math and then coming to the physics later. I don't have did I ever take a course that had relativity in it? No. So I hope that this has been helpful for the people who have these questions, but I also don't know exactly what I'm doing. So I'm sorry.
So it's the solution of the equation of motions with less symmetry than the equations themselves. That's
right.
Completely fine.
So I guess what makes it spooky is in this condensed matter thing that I'm going to talk about later. You have the models that are written down explicitly break relativistic symmetry, but then in some sense, in like the low energy approximation, it seems like it comes back, or at least the classification assumes that the relativistic symmetry comes back. And this is something that I really wish I understood better. Like what happened there? That's the kind of thing where I'm like, why I'm working.
Okay, let's see then.
Yeah. Sounds good. So topological field theory. Is a symmetric monoidal functor. From the boardism categories to flex vector spaces. So there's many variations on this. You could take like super vector spaces, Hilbert spaces. You could take all sorts of variants of the boardism category, but this is just what we're going to do today. So what this means is to an n-1 manifold, you get a vector space. And this is the state space. To a boardism, you get time evolution. Which is a linear, it's a linear function from state space to state space. Symmetric monoidal functor means that disjoint union goes to tensor product, which is something that you can think about from quantum mechanics. I have two things, I separate them by a big difference. What happens to their Hilbert spaces of states? You tensor them together. And the unit, the empty set, is sent to the complex number. And so this has one more nice consequence, which I said yesterday, but a little too fast. Let me say it again. So let's say M is a closed N manifold and has psi structure.
just to understand. So you're thinking about putting like a topological field theory in some manifold and then the formula?
Sorry. So for me, a topological field theory happens on all spacetimes at once. Like, so we're working with all possible n-1 manifolds and all possible borders at the same time. Yeah. So if you put it on a particular manifold, you'll get like a space of states. Did that answer your question?
Yeah.
Okay, cool. Who has more questions? All right. So a closed N manifold. So the boundary is empty. So in particular, this closed manifold is a bordism from the empty set to the empty set. So Z of M, whatever the topological field theory assigns, is a linear map from C to C. So one is sent to some number. This number is called the partition function. So when I say partition function, I mean it in the usual sense in quantum field theory, where it's like this is some number that we associate to a closed manifold in space-time dimension. So this kind of abstract formalism is nice because it wraps up a lot of the things we want to be true about quantum field theories all in one place. We get partition functions, we get state spaces, we get time evolution. And so I should mention this idea is due to Tia and Siegel. And then there's been, like I said, a lot of the variants where there's more category theory and whatever. There's been a lot of work on this, but this is the key thing that we're going to use.
Sorry, is there any reason why you dropped quantum from topological field theory?
Yes. Oh, great question. So a lot of people just call this topological quantum field theory, but it turns out that you can do classical field theory in this perspective as well. So I think the really shining example is Chern-Simons theory, where you so Dan Fried has a couple papers on classical Chern-Simons theory, where you replace this with a geometric bordism category, and then you get this gluing law with the Chern-Simons invariant, and it just works. But that's not a quantum field theory, it's classical. So in as much as this is a mathematical thing, and like what makes something quantum versus classical is kind of a slippery notion mathematically from this perspective, that's why I've been saying topological theory. But yeah, if someone says TQFT, probably they mean the same thing. Yeah.
Okay, so besides quantum gravity, is there any, why are you considering time evolution as something that can change topology?
Yes, that's okay. So here's maybe a right. So I have a good friend from graduate school who never liked this definition because of this question. And so it's a very valid question. Like if you're doing like quantum field theory and not quantum gravity, topology changing doesn't quite make sense, right? So here's the motivation that I've had for this, which is I want to compute this a partition function of this thing, right? In some quantum field theory. It's a topological field theory. Whatever the heck that means, this is local. So I should be able to chop up my manifold into a whole bunch of pieces. And then, at least heuristically, I should be able to compute the partition function on each of these pieces and then put it all together. And so, maybe it doesn't make sense for the topology to change. If I'm thinking of this as time evolution, but I think it's okay to say, okay, the partition function factors in some way when I cut it. And then on a manifold with boundary, like this one, whatever the partition function is, I should be able to, I need to choose data of a state on the boundary in order to get a partition function. So I get a map from boundary states to complex numbers, which is choose your boundary data, get a partition function. So this makes sense because this actually is turned around, right? So this is, because what is this functor assigned to this bordism? It assigns it. It's a linear map from the state space on the boundary to the state space of the empty set, which is the complex numbers. So from this perspective, this formalism is all a way of saying I can compute the partition function by chopping up a manifold. And on a manifold with boundary, to compute a partition function, you need some sort of boundary. And I hope this is like a good enough motivation that if you're working in a setting where there's not topology change. Do you think this, does this help?
Yes.
Okay, cool. Yes.
Also, like in quantum gravity, you're supposed to sum over all topologies, but you're not doing that here. Like you're just fixing a like, okay, you have these manifolds, you have a cobordism, and then you're assigning a partition function to a single manifold rather than, you know, assigning summing over all possible
Absolutely.
cobordisms.
So there's a couple things about that. First, there's this paper. I think it was one of Greg Moore's students who did this past year, who had this, but it might have been someone else, and I don't remember the name of the student who explored how that might look in this setting. So if I'm sorry for the vague description, I can go look for that paper later. It might answer your question. And second, you're right, but if we're investigating an anomaly of some sort of quantum gravity theory, then it makes more sense to say, well, I don't need to sum over things. I'm just looking at it I'm not looking at the quantum gravity theory itself, but rather its anomaly. And second, in that case, it still makes sense for the topology to change. But yeah.
Are you going to say what the partition function is in some example? Is it some kind of higher holonomy?
Wait, sorry, did you say in terms of higher holonomy?
In some examples? Like,
I was not planning on that. So my best understanding of higher holonomy is in non-topological theories. So I'm not sure that I would be able to do a good job of that. If you'd like to talk about it more afterwards, I'd love to. Yeah, because it's probably interesting, or something I think I find interesting. Who has more questions? Okay. So, right, so this is what a topological field theory is and
So I
why.
have another question.
What's up?
So what would change in the definition if the field theory was not topological?
So you'd have to fix the cobordism category. So right now, these size structures that I mentioned, they all nowhere in there is there any geometry. I've just chosen like an orientation or a spin structure. I've not chosen a Riemannian metric. I've not chosen connections. You know, I've not like, so if you wanted to fix this and make non-topological field theories, you would have to find a way of encoding these like geometric symmetry types and then define a category here. And honestly, there's like the technical details that I skipped over here get a lot more fun when you start throwing in geometry. And by a lot more fun, I mean much harder. So there's a few different answers. I know David Ayala has a paper about this. Adrian Clough has one. I'm forgetting a bunch of people. Oh, Konsevic and Siegel have one. There's a lot of papers on geometric cobordism categories, but it is much harder. And then you would also want to replace this with like Hilbert spaces. So in topological field theory, it doesn't really matter which one you pick, but in non-topological ones, it absolutely does. Yeah, great question. So now I need to tell you what it means for a topological field theory to be invertible. So let's start with, so a topological field theory is really a fancy version of, let's say I have a space X, and I consider a function from X to the complex numbers. Now, you know, that is F invertible in the sense of divide by F. Right, so there's inverses and going the other way, but that's never, like that's not in scope today. So there's sort of two ways to do this. So one of them is you could say F lands in the invertible complex numbers. This is a really fancy way of saying F of X is never zero. Right, the complex numbers are a field, every non-zero number is invertible. But if you have a function that avoids zero, you can divide by it. The other equivalent criterion is I could say there's a function g such that fg is equal to 1. So, okay, it is not super groundbreaking that these two things are the same. You know, you can, but what we're going to do is TFTs are fancy versions of this. And so we're going to do the same thing to define an invertible TFT. So this definition is due to Fried-Moore. So Fried is Dan Fried, Moore is Greg Moore. The paper is called Setting the Quantum Integrand of M Theory. The topological field theory is invertible if, and so we're going to start with the second definition. There's another TFT. So same dimension and same symmetry type. Such that E tensor Z prime is equal to the trivial theory. So I better say what this means. So the trivial theory is always, so Z of an object is always the complex numbers. Z of a cobordism is always the identity. But what does this tensor product mean? So tensor product is sort of pointless. So how did I define the product of functions? Fg evaluated at point x is f of x times g of x. And when I take the tensor product of topological field theory, that's saying I have a manifold here. I want to evaluate Z tensor Z prime on M. Let me actually write this over here. So whether M is an object or morphism, it's Z of M tensor Z prime of it. So invertible means that I can multiply it by something and get the trivial view. Equivalently, what's up?
Can you write the guys next to the arrow a little bit? Yeah.
Yeah, of course. Thank you. So yeah, thank you for letting me know. So I gave you a definition in terms of this characterization of invertibility, that you can multiply it by something, but it's also, you could also say it avoids zero. So equivalently Z is valued in the tensor product invertible subcategory of vect, which is one-dimensional complex vector spaces and non-zero maps between them. Right? Because if I have a function from C to C, I can divide by it as long as it's non-zero. So that's what an invertible topological field theory is.
Sorry.
Yes, what's up?
Regarding the first definition, so how should I think about the first definition in terms of partition function?
Great.
So how do I multiply partition function if I take a tensor product?
Oh, the partition function multiplies.
Just multiply.
Yeah.
But then you have to integrate over the configurations. Oh, how?
Well, so
you multiply the integrals or?
Great. Okay, so I should probably clarify. So this definition of topological field theory is kind of post hoc. Like you're not saying there's no partition. Sorry, there's no path integral. There's not even necessarily field. There's just the answer. Once you've done everything, there's the quantities you can calculate in the theory.
So then I should just think about numbers.
Exactly. So the partition function is some number, and there's some other number, and you just multiply them together. So in a way, it's very naive. Is that what you were trying to ask? Or
Yeah.
Okay, great.
Trying to understand what's this tensor product in terms of partition function.
Oh yeah. So the tensor product means multiply the two numbers together.
Okay.
Yeah. Were there more questions?
Is there a mention of a zero TFT?
Yes, it's not invertible. So I mean, you can just land everything. Oh wait. No, that's going to be a problem because you need to send the empty set to the complex numbers.
Right.
So
you
I
can
don't-
never have a TFT in which you send things to the zero vector space.
Right. So that would not be symmetric in model. So I don't think you can do that.
Okay, yeah.
Right, because the empty set has to go to.
Right, but just.
Yes.
Can you describe these invertible TQFTs in terms of the Frobenius algebra associated to them in the two-dimensional case?
Yes and
Because the
no.
Frobenius algebra has to be very, very naive.
Yes, it has to be. So, yeah. So for context, if you want to classify topological field theories in dimension 2, there's this nice theorem that they're the same thing as commutative Frobenius algebras. So first of all, to be an invertible, so this comes out as the state space of the circle. So your Frobenius algebra has to be one dimensional. And so then that turns out to suffice. What are the possible one-dimensional Frobenius algebras? There's you have to, what can the multiplication and co-multiplication and unit and co-unit be? There's some equations, and so that's the same thing. So there's really not very much interesting there. But the fact that there's not very much interesting is interesting. Yeah, that's a great question. So it's basically the one-dimensional Frobenius. Yeah, cool. Who has more questions?
So you wouldn't want any partition function with zeros.
Correct.
That's the message.
Yeah, exactly.
And what does it entail in practice that you don't have partition function with zeros?
So I think for me, the way that I think about this, I should probably write some of this down, is that the fact that the state spaces are one-dimensional. So this is a pretty serious condition. And like partition functions being non-zero feels like, I don't know, maybe you could satisfy that coincidentally somehow. But this is like really, you really have to try to make this true. This is sort of straying away from the question. I will get back to it. And so I think of these. Because of where we are, I'd like to abbreviate this with IFT. So let me say, so T is the invertible field theory.
That's a great logo. Yeah.
Okay, cool. Unfortunately, I don't have anything that can stand for ICMAT. Maybe I'll think about it over the break. So I think of these things as almost but not quite trivial. And so getting back to your question, how do we know that they're not trivial? Well, you look at these partition functions and you get something other than one. And so, the fact that they're non-zero is maybe not so it's nice, but it's not so staggering. And it's the fact that they're not one, which is like, oh, cool, I have something interesting here. So this fact that they're almost but not quite trivial, a lot of applications of IFTs come from this. So that is, there's a lot of cases where we study invertible field theories and do something with them. And why do we do that? Sometimes it's because the thing we care about really is invertible, but a lot of the time it's because whatever question we want to do is way too hard. So let's study the simplest possible non-trivial case first.
Is it possible to go from a TFT to an invertible TFT by taking the determinants of it in some case?
That's a great question. I don't know of a way of doing that. That would be very cool, but yeah. In general, I know how to go the other way, like you gauge some symmetry, and that leaves invertible land. But okay, so I should probably give you an example. Oops. So it's difficult to write a lot of these down explicitly, just because like a topological field theory is a very complicated thing. There's a lot of data there, and you have to really engage with what does it mean to be symmetrically nodal in the sense that I told you not to worry about. But invertible field, so example is the Euler TFT. Let's pick lambda a non-zero complex number. And so what I'm going to send an object to, I'm just going to send it to complex numbers. I'm not just going to say, oh, some one-dimensional vector space that's complex numbers up to isomorphism. I mean the complex numbers on the nodes. So what do? I say that if I have some bordism, so here's X incoming. So what I want to assign to this is a map from the complex numbers, the state space here, to the complex numbers, the state space here. And that's going to be, I'm going to take the Euler characteristic of this thing relative to the incoming boundary. That's some number. And then I take lambda to the power of that. So what are some things we need to check? We need to check, is this, does this compose correctly? And the gluing formula for the Euler characteristic means that this does. So we also have to check that it's symmetrically nodal. And that follows again, how does the Euler characteristic behave under disjoint unions? And finally, is it invertible? This is one-dimensional. This is always non-zero, so we're good. So this is kind of a silly example of an invertible field theory, but it is one. And I figured if I didn't give you an example, it would not be good.
Sorry, what is the subscript there in the?
Oh, this says incoming. Let me write that larger. So the idea is this cobordism has an incoming and an outgoing boundary. Is that large enough, especially for the Zoom audience?
Yeah, fine.
Okay, cool. Yeah, I don't know. So my dad said based on my handwriting alone that I should go into medicine. So you know, I always want to check these things. Were there more questions? Yes.
IFTs form a group, right?
Yes. Oh, yeah. That's something that I should say. So they're not just that they're an abelian. So yeah, thank you for mentioning this. So if you fix the symmetry type in the dimension, you've got this abelian group. So now we have an interesting math question. We compute this. And so I wouldn't ask it that way if the answer were at least completely no. But first, I think I'm going to maybe detour into the condensed matter stuff a little bit before coming back to this question. So it turns out the answer is yes. There's this like this is one of these like honestly one of my favorite parts of like modern homotopy theory of manifolds is that is an answer to this question. So before I change to condensed matter stuff a little bit, are there any questions?
Yeah, the other characteristic that you're using there is just the ordinary one. I don't understand the first entry. So is the other characteristic of X?
Oh shoot, everything is the same symbol. So this is the relative Euler characteristic. So what this means is you take the relative homology of this against this. So like you sort of quotient this down to a point, and then you compute the Euler characteristic. Yeah, thank you for clarifying. More questions? Actually, you know what? I'll start over on the other board. So I want to talk about a classification question in condensed matter physics, which ends up asking about invertible field theories. So the condensed matter theorists are interested in these things called topological phases of matter. So I'm a mathematician by training. I'm still a mathematician. I don't know a lot about the physics aspects of this. But what I can tell you is that the people who study condensed matter like materials discovered, in the last like 30 years or so, they discovered these weird things where you take this particular metal alloy or crystal or something, you cool it down to a specific temperature, maybe you apply an electric field, and you get this bizarre behavior. For example, maybe you drop an electron in and it looks like it splits into 3 particles with charge 1/3. Now, okay, the standard model, modulo questions about the W boson still seems to work. So like there's no 1/3 electron. What's going on here? And the answer is that these things have these weird patterns of entanglement where you have this big sea of electrons and inside it makes the most sense to model, it makes sense to model this pattern of entanglement as if it were a particle. It's localized in some way. But that is, even though that's not actually what's really happening. So the point is you get these systems with kind of bizarre behavior. And so there's this question of how do we model and classify? So this is both a theoretical physics question and then a mathematical question. Maybe we can start with, depending on how much this question would it require engaging with making quantum field theory rigorous, maybe we can extract some good math here and solve it. So how do we model them? Often is lattice Hamiltonians. So you take space, this is a non-relativistic system. You take space, you chop it up into like triangles and lines and dots, or maybe maybe a CW structure if you're being ambitious, and you build a state space in a Hamiltonian purely from the data of this triangulation. So we want these to have a spectral gap. And there's a little more to say here, like what makes the system a topological, like what makes it have this property that it's a topological phase, what, as opposed to some other thing. There's a lot of like difficult questions to trip over that like aren't really solved.
Maybe you should write a little bigger.
Yes,
for
okay, thank you.
people into-
Okay. And then we'd like to consider equivalence classes under some sort of deformations, preserving the spectral gap, or such that the gap doesn't close. So I'm being super imprecise here, and that's in part because a lot of this is just it's difficult to understand even at a physical level of rigor. Questions like, what is a phase? Like, what makes this thing a topological phase and this thing not a topological phase? Like, what kind of equivalence? What does it really mean to have a spectral gap? How do you define this precisely? These things are difficult questions without answers, but unfazed, we still carry on. So then there's the question of classifying. So I'd like to say, take a space of Hamiltonians. Sure, whatever. Remove the gapless ones. And take pi 0. But again, we're really far away from being able to do this. That requires butting our heads against these difficult questions straight up. And it seems like this is not just difficult because for the same reason that making quantum field theory mathematical is difficult, but there's also a few genuinely new surprises in condensed matter physics. So like fractals, what's a good way to rule out fractals? I think this is just, I think people are working on this, but it's not clear what the answer is.
Did you mean rule out?
What?
You said rule out?
Yes, there's these things called fractons, which look a lot like they should do this, but they're not topological enough. Or I guess different people have different perspectives, but it is my opinion that several of their crucial properties, such as a dependence of the space of ground states on the size of the manifold, means that we should exclude them. But I don't think there's a good way to say, oh, this definition includes no fractals. Like, we don't know how to do that. So I admit I don't know a whole lot about fractals. So it's mostly a sort of a thing that I want to avoid, but other people think other people have different perspectives that they should be like celebrated and studied more, which is good. So what we're going to do instead of this, how might we model topological phases? So it is believed that at low energy, actually, sorry, before I say that, so in the condensed matter literature, these are studied with all sorts of tools. So for example, maybe you say, okay, well, let's take some continuum limit and study these things there. Maybe let's actually just try and work with study deformations of these Hamiltonians. There's lots of different ways of studying this, different formalisms. And so you get lots of classifications. Where again, you fix the dimension and you fix what kinds of symmetries you want.
Okay, are we still on compact manifold?
I have not said anything well-defined enough for that to have a valid answer.
Sorry, I am also confused. When you say symmetry, you mean gauge symmetry?
Let me answer this in a little more detail than that. So I said different people study this in all sorts of ways. So as far as I'm concerned, yes, you have to work on compact manifolds. But there's a lot of people for whom study this topological phase means do it on just an infinite square lattice. So it depends who you ask. As for your question, I mean things like I have a Hamiltonian. What kinds of symmetries does it have? Does it have a time reversal symmetry? Does it have a particle hole symmetry? Or does it preserve fermion parity? Is there a group acting on the state space at each point? Those kinds of symmetry. So usually it's not as explicitly a gauge symmetry though. I mean, sometimes that happens, but usually not. More questions. So one thing which I should mention is it's possible. So there's this there's a tensor product on topological phases. And again, I want to reiterate, this is the sort of the legalese disclaimer. And I have to say this because I'm a mathematician. So when I say something is true, but we don't actually know that it's a theorem, someone watching somewhere is going to be unhappy. And so I want to clarify that pretty much all of this is a heuristic. Parts of it are known at physics levels of rigor, but most of it is even still up in the air there. We're just trying to get some understanding. And there's different formalisms that know some things, but not others. But in any case, you can stack topological phases together. And so you put them both on the same medium. And you say that there's minimal or no interactions between them. So this allows you to take two topological phases and build a new one. So you can now ask about invertibility with respect to stacking. Can I stack my phase with some other phase to obtain the trivial phase? So and I don't mean trivial phase on those. I mean, I get something and then I can deform the Hamiltonian without closing the gap to obtain the trivial phase. So invertible phases are also called SPT, symmetry protected, topological, phases. I've also seen short-range entangled phases. And I've also seen people who say that SPT stands for symmetry protected trivial. So just this is like reader's guide. People will use all of these terms in the literature. I think invertible phases is the most accurate. SPT also is one of the most common. So just heads up that that's what these things are. So, but the point is, like what I just erased, whoops, topological phases, there's a lot of them, they're confusing, the classifications we know are complicated. So let's look at invertible phases first. So, invertible phases seem like a good testing ground for our models. In physics and mathematics, however we're studying these things, invertible phases are a good place to start. And so in particular, the physicists agree. Lots of papers computing these abelian groups of invertible phases. And again, they use all sorts of techniques and they work in different dimensions and with different symmetry types. So, okay, but now we have a question, a mathematical physics question. Can we mathematically model these things? Is there some general formalism where we say, we think that an SPT phase is given in this following way? And then, okay, we compute a bunch of groups of them and match what the physicists get. So is that something we can do? And the answer is yes. But it's not just, can we reproduce these things that the physicists do? It's a test for all of this mathematical formalism for field. So it's believed that at low energy, topological phases are well approximated by topological field theories.
How low?
I don't know that I have a good answer to that question. Yeah, at low energy, sorry. Oh yeah, sorry, yeah, has to be like, you have to get rid of the, you essentially blow up the spectral band. Yeah, whoever said that, thank you.
Wait, what's the reason for the name Symmetry Protected?
Can I tell you after, like, for reasons of time, I don't want to get into it, I'm sorry. So, okay. So it turns out that stacking passes to the tensor product of topological field theories under this heuristic. So if you're an invertible phase, you're approximated by an invertible field. So this is good because we have a mathematical object. So compute groups of invertible field theories and compare to SPTs. And do they match? So this is a good way to test, okay, how good is this classification? Do we have the right mathematical model for topological field theory? Yes.
I think that what's the definition of topological phase?
I did not define it. Just they are these systems that I don't know of a good definition for. So if you look at the condensed matter literature, especially in the theory literature, people will have answers, but I think there's like there are partial definitions, or like people are still working out the theory. I wish I could give you less of a wishy-washy definition over there. Yeah, who has more questions? Okay, so, okay, well, what happens here? So this mathematical story, the classification of invertible field theories, is due to Fried, Hopkins, Telemann. And they build on this really delightful work of fallacious mathematical advice. So what you end up doing is you compute, so I had this, like, these things are functors from a Bordism category to something else. You end up computing the homotopy type of the Bordism category in a specific sense. And U means GMTW. And also Nguyen, who took into account, so they essentially did this for ordinary functors, and then Nguyen said, okay, well, symmetric model is important, let's do that. Their papers are in very different words. It is Fried, Hopkins, Telemann who expressed it in this way. So do they match? No, but that's okay. You know what we haven't done yet? We haven't said anything about unitarity. And once you take into account unitarity, then they do match. So this is this paper of Fried Hopkins. They're really long 2016 one, where they say, what does it mean for an invertible field theory to be, well, not unitary, but because we've Wick rotated the Euclidean signature, it's reflection positive. So they classify reflection positive invertible topological field theories, and they notice that these match the groups of SPTs that the physicists have come up with. In fact, reflection positive invertible field theories. So the abelian group of reflection positive invertible field theories in dimension n on psi manifolds. So again, if you want to classify SPTs, you have some collection of symmetries that you care about, like time reversal, fermion parity. And so you pick your psi structure to match them. And so this classification is the set of torsion, Bordism, invariance into the non-zero complex numbers. So if this group is finite, this is the character dual, the Contragon dual. If this group is infinite, you throw out the free part and you just keep the torsion part and then do the same thing. So if you can compute Bordism groups, you know what the groups of SPTs are. So just as I have enough time to do one very brief example, which is the Majorana chain.
Just a question. So by groups of IFTs, do you mean a group in which IFTs are the elements of the group, or is it like you fix an IFT and then you have a group associated to that?
So I think you were the one who asked. It's like the classification. These things form an abelian group. It's that abelian group.
Okay.
Yeah. Sorry. So the quick example I'll give is there's this object called the Majorana chain, the Katayas, and it's a 1 + 1g fermionic SPT. And you consider it with or without a time reversal symmetry. So in that case, if you consider it without, the physicist said there's a Z mod 2 of these, because 2 times this is 0. With, you get a Z mod 8. I don't remember who did this, but this one is due to Fitkowski, Katayas, and also Turner, Ullman, Berg. So they did this, using, like, they spent a lot of time like actually looking at the lattice system and playing with Clifford algebras and the like, but at low energy. So without corresponds to this second spin-Bordism group. So and this is Z mod 2, which I think is due to Milner. And so you would say a priori, okay, these things without time reversal, this corresponds to torsion Bordism invariant. So the second spin Bordism group, and then we already knew that Z2, so these match. And if you include this time reversal symmetry, this is the second pin minus Bordism group. So T² = 1. You'd want psi to be the particular pin minus structure rather than pin plus. And wouldn't you know it, that's Z mod 8. So sure enough, by doing these Bordism computations, which have been standard in mathematics for the last half century, you can explain the things that the physicists did. So the model is working, and you can make new predictions. So I am out of time. So thanks so much for listening, and please let me know if you have more questions. Yes.
Is there any reason why you have this match between this abelian group of invertible topological field theories and this I mean, is there
where did that come from?
Something like quantum gravity behaves in some way as a topological phase of matter in some sense?
So my best understanding for this is I don't know how to relate it to quantum gravity. So my intuition for this is that, so this thing is the partition function. So to every closed end manifold, you get an object. And so I guess the content is that if you have a unit, a reflection positive invertible topological field theory, oops, I forgot to say topological. So then the partition function is a Bordism invariant. And there's this paper by Kazuya Yonakura where he argues this sort of by hand. So Fried and Hopkins do a whole bunch of like high-flying homotopy theory. But like I said, Yonakura's paper, I think, more directly says, why should the partition function be trivial on a manifold of grounds? So once you know the partition function is a Bordism invariant, the second question is, why does every Bordism invariant give you a field theory? Which is a little more complicated, but I guess that's my intuition for this. Honestly, if there were a nice intuition relating to quantum gravity, I think that would be very cool. I just don't know what it would be. It's a great question.
So the SPTs, are they in the same dimension as a TFT?
Yes, right. So to study topological phases of matter, you pick a dimension of your system and you pick what symmetries you care about. And to study topological field theories, you pick a dimension and you pick a psi structure, so you can define a Bordism category. And so these have to match. So the caveat is the Majorana chain takes place on a circle. So space is one-dimensional, and space-time would be two-dimensional. So the Majorana chain takes place on space. We've broken relativistic symmetry. But when we classify these invertible field theories, we're looking at something, we care about the space-time dimension, and we put relativistic stuff back in. So that's the thing I mentioned earlier, that I don't know how that came back. But the point is, the space-time dimensions have to match. Also, you would want to know what SPT stands for, like why is SPT? So initially, people looked at these and they said, okay, we have these phases, and if we add some extra symmetry, like an internal G symmetry, then we get something that is non-trivial. But if we forget about that, it is trivial. So symmetry protected trivial, or symmetry protected, as in unless you have the symmetry, it's trivial. So symmetry protected topological phases. It turns out in high enough dimensions, you can have invertible phases, which are not trivial when you forget about your symmetry. So this is not quite the right word, but you know, I don't think it's my place to tell the entire condensed matter theory community that they're wrong. So you know, SBT is a nice acronym. It slides off the tongue a little better than invertible phases. Were there more questions?
Okay, let's do the other question for coffee. Remember, we have the coffee.